sometimes it makes it easier to calculate the integral in cylindrical or spherical coordinate system. When it comes to cylindrical coordinate system, any point is represented by r, theta, and z. R is the distance between the origin and the point in xy plane. Theta is the angle in xy plane, and z is basically your z value. X is r cosine theta, y is r sine theta, and z is equal to z. This is basically the polar coordinates that we learned before. R squared is x squared plus y squared. Tangent theta is y divided by x, and z is equal to z. Now, for spherical coordinate system, it's a little bit different. You have a point in the space, and these are the cylindrical coordinate system that you learned here on the left-hand side, and these are the spherical coordinate system. Rho is the distance between the point and the origin. Theta is the angle in xy plane, or the projection of your point in xy plane. Note that phi is the angle between the positive part of z-axis, and it goes at most to the negative part of z-axis. It doesn't have the full rotation. That's the important note here. By convention, phi ranges between positive part of z-axis or 0 to pi or 180 degrees. So spherical coordinates is denoted by rho, theta, and phi, the way that we define x. X is rho sine phi cosine theta. Y is rho sine phi sine theta. And z is equal to rho cosine phi. And as we mentioned, rho is the distance between the point and the origin, or rho squared is x squared plus y squared plus z squared. So in cylindrical coordinate system, any point can be represented by r, theta, and z. X is r cosine theta, y is r sine theta, and z is equal to z. Suppose you have an object in the space. From top, it's bounded by a function of x and y, u2. From below is bounded by another object or another function in x and y. If you look at the projection in xy plane, this is the base that is projected in xy plane. So as you can see, it looks like a piece of cylinder. When you look at the projection, it seems like it's part of a sector of a circle. Theta is bounded between alpha and beta, and your r is bounded between h1 and h2. So in that case, you can easily calculate the volume. The element of the volume is, first of all, you're going to write down the function itself, f of r cosine theta. X is r cosine theta, so wherever you see x, you're going to use r cosine theta. Then for y, you have r sine theta. Wherever you see y, you're going to substitute that by r sine theta, and z stay the same. There is no change in your z. And the volume element is dz, z bounded between u1 and u2, r, dr, and r is bounded between h1 and h2, and theta, which is bounded between alpha and beta. So one important piece is that the volume element is r dz dr d theta, or dz r dr d theta. Let's take a look at one example here. So this is the formula that we introduced for cylindrical coordinate system. Question says evaluate the triple integral of x squared plus y squared dz dy dx. Your z is bounded between square root of x squared plus y squared and 2. Y is bounded between negative square root of 4 minus x squared and square root of 4 minus x squared. and x is bounded between -2 and 2. Let's take a look at the visualization a little bit. So here you have z equals to 2, which is your plane. Z equals to square root of x squared plus y squared. So this is the visualization of z bounded between 2 and square root of x squared plus y squared. But when y is bounded between negative square root of 4 minus x squared and square root of 4 minus x squared, this is basically a cylinder. And your x is bounded between -2 and 2. So this is what we are calculating, the triple integral of this surface bounded by these elements. So first of all, let us identify E, the region that we are taking the integral over. Z is bounded by, from top, by z equals to 2, and from bottom by z equals to square root of x squared plus y squared. What about our y? Y is bounded by square root of 4 minus x squared, and from left by negative square root of 4 minus x squared. And as you see, x is bounded between -2 and 2 given in the question. Since you have a cylinder involved, it's better to use cylindrical coordinate system. So in calculating this triple integral, let us do the conversions. X is r cosine theta, y is r sine theta, and z is equal to z. Okay, so for E, z is bounded between 2 and square root of x squared plus y squared. And this is our object that we're looking at. If you look at the projection in xy plane, the intersection between all of these is this guy on the right-hand side in 2D, 2 dimension. So if you convert this into cylindrical coordinate system, x is r, y is theta, z is z, but make sure you do the conversion. But instead of x, we're going to write down r. Instead of y, we're going to write down theta, and z is equal to z, and we have to do these conversions. Take a look. Now your z is bounded above by 2. 2 doesn't change. And from left, it was bounded by square root of x squared plus y squared, which is now is just r. Why is that? Wherever you see x, you're going to use r cosine theta. Wherever you see y, you're going to use r sine theta. So r squared cosine squared plus r squared sine squared is simplified to r squared. Square root of r squared is just r. So we found the boundary for z. Now for y, y from below is bounded by negative square root of 4 minus x squared, and from above bounded by 4 minus x squared root, and then x is bounded between -2 and 2. So by looking at our 2D object, which is the base, this is basically saying that, hey, r is bounded between 0 and 2, and theta is a full rotation between 0 and 2 pi. Remember that this guy here is x squared plus y squared equals to 4, which is basically a circle centered at the origin with radius 2. So that's how you get r bounded between 0 and 2. And as you can see, theta is bounded between 0 to 2 pi because you have a full rotation. Now let us do the calculation. The triple integral over this region in xy plane, we saw that E can be converted into polar form using cylindrical coordinate system. So x squared plus y squared is nothing but r squared because r squared cosine squared plus r squared sine squared is equal to 2. We just do the substitution here. Then you take the integral with respect to z. Z is bounded by r and 2. Then r dr, taking the integral with respect to r is bounded between 0 and 2. And for the theta, as we saw, it's bounded between 0 to 2 pi. And again, please pay close attention. The volume element is r dz, dr d theta, must be the same in your calculation. Okay, if you do the multiplication, you get r cubed, and then you have the integral of dz, z bounded between 2 and r, so you get 2 minus r, and then you take the integral with respect to r. You can separate d theta as well, because your function doesn't have any connection between r and theta. Then distribute r cubed into parentheses and do the calculation. You get a half r to the 4th minus a 5th r to 5. Again, make sure to distribute r into parentheses. You have r to the 4. The integral of r to the 4th is 1/5 r to the 5. And r is bounded between 0 to 2. And the integral of d theta, when theta is bounded between 0 to 2 pi, is 2 pi. Once you do the calculation, it is 16 pi over 5. So as you saw, converting everything into cylindrical coordinate help us to make the calculation a little bit easier.